Have you ever wondered how you could possibly define an infinite flat surface in 3D space with just a single equation? Well, that's exactly what we're tackling today, the equation of a plane. It's a core concept in multivariable calculus, and we're going to demystify it.
Okay, so here's our game plan. First, we'll uncover the secret ingredient that makes this whole thing work. Then, we'll turn that idea into a usable formula. After that, we'll take on a classic problem where you only have 3 points. Then, we'll analyze the relationship between a line and a plane. And finally, we'll wrap up with the one core takeaway you absolutely need to remember.
All right, let's kick things off with the single most important concept for understanding planes. Now, I'll warn you, it's a little bit counterintuitive, but I promise, once this clicks, everything else just falls right into place. So this is the big challenge, right? A plane stretches on forever in all directions. It's not like a line with a clear start and end. So how in the world do we lock it down? How do we capture its exact position and its tilt with one clean equation? You know, our intuition from working with lines kind of gets flipped on its head here. For a line, you need a vector that points in the same direction, right? A parallel vector. But for a plane, a parallel vector doesn't help at all. I mean, you could just spin the plane around that vector forever. The real key, the secret, is a single vector that sticks straight out of it, perpendicular to the surface. That's what locks its orientation in place. And this special vector has a name. It's called the normal vector. We usually just call it n. Now, what makes it so special is that it's orthogonal, or perpendicular, to every single vector you can draw on that plane surface. And that little fact at the end, that's the mathematical engine that drives everything. Remember, a dot product of 0 is the ultimate test for two vectors being perpendicular. Okay, so we've got the concept of the normal vector down. Now let's see how we can build on that idea and turn it into a practical formula that we can actually use to solve problems. So these are our two main tools in the toolbox. The scalar equation is what you build first. You use a point on the plane and the normal vector. Then, if you just do a little algebra, distribute the a, b, and c, and move all the constant numbers to the other side, you get the nice, cleaned-up linear equation. And notice the most important part. In both forms, the components of the normal vector, a, b, and c, are always the coefficients of x, y, and z. That's a huge shortcut. All right, let's get our hands dirty with a classic example. Here, we're given everything we need on a silver platter, a point that we know is on the plane, and the normal vector that tells us how the plane is tilted. Our job is to find the equation. So we just take the components from our normal vector, that's 3, -5, and 2, and they become our a, b, and c. Then we grab the coordinates from our point, 2, 4, -1, and plug them in for xo, yzo, and zzo. And from there, really, it's just algebra. You expand all the terms, gather up the constants, and boom, you've got your final equation in standard form. Okay, that last example was pretty straightforward, but what happens in a much more common situation where you aren't just given the normal vector? What if all you have are 3 random points just floating in space? Let's figure out how to find the plane that connects them all. So here's our puzzle. We've got 3 points, P, Q, and R. We know for a fact that there's one unique plane that passes through all 3 of them. But to get its equation, we need that normal vector. So, how do we build it from scratch? This is the strategy, and it's a brilliant one. We'll start by creating 2 vectors that actually lie flat in the plane. For instance, we can make a vector from point P to point Q, and another one from P to R. Then, and here's the magic, we take their cross product. Remember what the cross product does? It gives you a brand new vector that's perpendicular to the first 2. And if those 2 are in our plane, their cross product has to be our normal vector. It's the perfect tool for the job. Okay, let's run the play. Step 1, find the 2 vectors in the plane. Easy enough. Step 2, calculate their cross product. This gives us our hard-earned normal vector, 6, 3, 2. And look at that, we're right back to the same kind of problem we had before. We just pick one of our original points, P is a good choice, and use our new normal vector to build the scalar equation. A little simplifying, and we get our final answer. So far, we've been all about building planes. Now, let's switch gears a little. Let's use what we know about the normal vector to analyze how other things, like a line, might interact with a plane that we've already found. This is a really good conceptual question. Orthogonal just means the line hits the plane at a perfect 90-degree angle. Think of a pin pushing straight down into a piece of cardboard. Is that what's happening here? Let's find out. To answer this, we need to play detective and pull out the 2 key clues. From the line's equation, we can see its direction vector, v. And from the plane's equation, we can grab its normal vector, n.
just by looking at the coefficients of x, y, and z. So now we have the two vectors that define the orientation of both of our objects.
And here's the logic that ties it all together. Now, this might feel a little backwards at first, so think it through. If a line is perpendicular to the surface of the plane, then the direction it's traveling in must be parallel to the normal vector, which is already sticking straight out perpendicular to the plane. So our big question really becomes a much simpler one. Is the line's direction vector parallel to the plane's normal vector? And we can test for that just by seeing if one is a scalar multiple of the other. And in this case, well, would you look at that? The plane's normal vector is exactly 2 times the line's direction vector. That confirms they're parallel, which means, yes, our line is in fact orthogonal to the plane. Wow, we have covered a lot of ground, from building equations from scratch to analyzing how lines and planes interact. So let's boil it all down. What is the single most important idea from this entire explainer? This is it. Everything, and I mean everything, comes back to the normal vector. If you have it, or if you can figure out a way to find it, the rest is just plugging numbers into a formula. The point tells you where the plane is in space, and the normal vector tells you how it's tilted. Get those two things, and you can define any plane in the universe. And that brings us to one last thing to think about. You've mastered a single plane, which is a huge step. But of course, the universe is full of them. So what happens when two of these infinite surfaces slice through each other? What kind of shape do they create? And how would you even begin to define that? Well, that is the next exciting chapter in your journey through 3D space.